Okay, so we just finished showing that this was not continuous at -3. And as we said about in this class, not for all of mathematics, but in this class, when I give you, or if I give you, or if the textbook gives you a piecewise defined function and asks about continuity, what we are going to be concerned with is the numbers involved in the restrictions. Now, that's not the way it has to be mathematically, but at this level, Calculus 1, what we're going to concern ourselves with are the numbers involved in the restrictions. And so in this case, -3 and 3. And the answer is always going to be continuous for all reals, except maybe at these two, at the numbers involved in the restrictions. So what we have found so far, we tested -3. We went through our went through 2 of our conditions of continuity. We found that the limit didn't exist, and so we could conclude that the function was not continuous at -3. Now we need to do the same thing with x = 3 and test those conditions. So number 1 is f of 3 defined? Well, just go into the function and see what f of 3 is. So if I bring it back down here, when x is 3, I'm supposed to use this rule here, 1 over x plus 3. And that's what this is saying. If x is 3, use the rule 1 divided by x plus 3. So f of 3 will be 1 over 3 plus 3 for 1/6. So condition 1 is satisfied. Because all condition 1 is, do you have a function, or do you have a functional value? And yes, I have a functional value. Let's see if I can get that to focus a little bit better. A little bit. I'm working from my office this time instead of a classroom. Okay, I'm going to copy my function down again so we can just still have it on the same piece of paper. And so it was f of x. Sorry if that's so crooked. I'll try to make it less crooked for you. F of x equals, and the function was this, x minus 3 over x squared minus 9. If x is not equal to -3 or 3, it's equal to e to the x if x equals -3, and it's equal to 1 over x plus 3 if x equals 3. Okay, so we looked at condition 1, the functional value. There was a functional value. So let's go on to condition 2. Condition 2 is, does the limit as x approaches 3 of f of x exist? Well, let's find that limit. Well, now we have to be smart on this. Sorry about the crookedness here. There we go. We have to be smart on this. This is a two-sided limit, but when I look at my graph up here, I got to decide what I need to do for that limit. And remember what this means. Two-sided limit, which is not going to play a terrible issue here, but we got to remember what this means. That means close to 3, but not equal to 3. And in that case, when I'm not equal to 3, that means I'm going to be using this top branch here, that I use x squared minus 9, x minus 3 over x squared minus 9. So the limit as x goes to 3 of f of x is the limit as x goes to 3 of x minus 3 over x squared minus 9. You could substitute. Substitution would give us 0 over 0. And we know that 0 over 0 as a limit is absolutely meaningless. And so we will factor instead. And then I get some nice canceling here. The x minus 3's cancel. And so, let's see if that focuses a little bit better for us. And that's the limit as x goes to 3 of 1 over x plus 3. And now I can substitute. And I get 1/6. So condition 2 is satisfied. Condition 2 is I just want to find a limit. Got it, got a limit. So now I move on to condition 3, which is does the limit as x goes to 3 of f of x equal f of 3? And indeed, that's a big yes, that the functional value was 1/6, the limit was 1/6, so 1/6 equals 1/6, so condition 3 satisfied. And so it is continuous at x equals 3. So then the total answer, so f of x is continuous for all reals except x equal -3. The first number that we checked out, that we ran through the conditions on -3, and we decided it was not continuous at -3. Then we ran through the conditions at 3, decided it was continuous at 3, so it's going to be all reals except the -3. And if I had to do interval notation, which on a test I don't particularly care, but if I had to do interval notation, there would be the answer of interval notation, in interval notation. Now again, what we really care about, or not really care about, but in this class, we've cut this down from what you could see all of mathematically. In this class, when you're given a piecewise defined function, the answer is always going to be some version of continuous for all reals except maybe the numbers involved. And here, the numbers involved -3, it was discontinuous, 3, it was continuous. So we ended up with all reals except -3. Okay, last question in this section. So there are my 3 conditions of continuity again. Function is continuous at x equal a. See if I can get this without falling off my desk here. And make it look, we'll zoom in a little bit so we can see it. Try to make it, boy, this is my first time making a video for my office, and this isn't going particularly well, is it? Yeah, that's about the best we're gonna do. Let's zoom in, and we'll see if we can straighten it a little bit. It doesn't want to zoom in particularly. Okay, well, let's just get rid of this piece and see if that'll work. Okay, so there are my 3 conditions of continuity. It won't zoom in anymore on that for me, but that's okay. F of a is defined. Oh, there we go. Oh, there we go. There are my 3 conditions of continuity. A function is continuous at x equal a, and I'm sorry, it's a little blurry, but you should have these down in front of you. If function is continuous at x equal a, if you have those 3 conditions, 1, f of a is defined, the limit as x goes to a of f of x exists, and the limit as x goes to a of f of x equals f of a. So there are my 3 conditions of continuity, blurry as it is. Those last, all 3 of those conditions could be summarized in just the 3rd condition. And indeed, in advanced textbooks, they'll have just that 3rd condition. But what this 3rd condition, but I still want you to know all 3, and that's on the test, know all 3 of those. But what this 3rd condition is implying is that you will have continuity if you can get the limit by just substitution. So that's kind of what f of a is saying there. F of a is saying plug in a into f. And so you are guaranteed continuity if you can get the limit by direct substitution. Now, that is not to say that if you did something else to get the limit, that it's still not continuous, but you're guaranteed kind of a shortcut for some problems, that if you can do the limit by direct substitution, you do have continuity at that point. Now, again, that's not to say that if you did the limit some other manner that you won't have continuity, but if you did direct substitution, you will have continuity. So last problem, find the limit. Is the function continuous at the point being approached? So doing the limit, we start by just always substituting in. So that's going to be sine of 4 pi over 3 cosine of tangent of 0. And now we just start working that out one step at a time. So I'm going to start right there with tangent of 0. And if you need to, you go off to the side and figure out what tangent of 0 is. Tangent of 0 is sine 0 over cosine 0, which is 0 over 1 for 0. So this becomes sine of 4 pi over 3 cosine of 0. Then you figure out cosine of 0. Cosine of 0 is not 0, it's 1. So then I have sine of 4 pi over 3. And then you just figure out what sine of 4 pi over 3 is. And sine of 4 pi over 3 is in the third quadrant. Sine is negative in the third quadrant. And sine of 4 pi over 3 is negative square root of 3 over 2. So there's my limit. And then because, so the second question, is the function continuous at the point being approached? Because we found the limit at x equals 0, I guess it's theta equals 0. Theta equals 0 by direct substitution. The function is continuous at theta equals 0. And that's the end of this section. Again, I want to reiterate, when it comes to the test, I am going to ask you to state those three conditions of continuity, that f of a is defined, the limit as x goes to a of f of x exists, and the limit as x goes to a of f of x equals f of a. And that's the end of this section.